Okay, so this is Unit D, Atomic, Nuclear, and Particle Physics. So in Unit D, there's 4 outcomes. The atomic physics part is outcomes D1 and D2. The nuclear physics part is D3, and then the particle physics part is D4. In the gradebook, D1 and D2 are grouped together, so you'll just be getting 1 grade for D1 and D2 together. So for the next few lessons, we're going to be working on D1 and D2, which is atomic physics. So today we're doing lesson 1, the Dalton, Thomson, and Rutherford models of the atom. So, introduction to atomic physics. So in atomic physics, what we're really studying is how atoms behave and what an atom would look like if we could see it. Now the problem is we can't observe atoms directly. What that means is because atoms are too small, you can't just open an atom up and look inside if you want to know how an atom looks. Instead, you have to come up with some other type of experiment to study atoms. And that's what this section is about. We're going to look at different experiments that have been done over the years. And every time a new experiment is done, our understanding of the atom improves a little bit. So our understanding of the atom has changed over time. So here we have a bit of a timeline of all of the different models of the atom. The oldest model, and the first one that we're going to look at, is called the Dalton model. It's also called the indivisible model because Dalton thought that atoms were indivisible. Then we're going to look at the Thomson model, which is sometimes also called the raisin bun model. Then the Rutherford model, which is also called the planetary model. Then the Bohr model, and finally the quantum model. So when we're going through these models here, I'll just go back for a second. Instead of memorizing what the model says, because we're in Physics 30 and not Science 10 anymore, it's really important that we actually learn about the experiments that were done and try to understand how the evidence collected in the experiment tells us about an atom. So the focus here is really on the experiments and what the experiments show, not just on memorizing the end result. So beginning with Dalton's model of the atom. So actually for the Dalton model, there is no experiment to know. You just have to know what Dalton said. But for the next few models, we'll be looking at experiments. So Dalton said that atoms are indivisible spheres. The word indivisible means that you can't break down an atom to something smaller. Okay? This was sometimes called the billiard ball model because Dalton pictured an atom as if it was a billiard ball. So when Dalton said that atoms are indivisible, what he really meant is that he thought atoms are the smallest things that exist. So that means, according to Dalton, there are no smaller particles within an atom like charges. Of course, today we know that that's not true. We know that atoms are made up of electrons and protons and neutrons, but at Dalton's time that was not known yet. Okay, so in the Dalton model of the atom, very important, there's no charges involved. And the Dalton model had to be revised or changed due to Thomson's experiment, which is what we're going to look at next. So Thomson's cathode ray experiment. This one you do have to know the experiment and what the experiment showed. So what you should do before continuing with this video here is you should actually go watch this YouTube video. So pause me, go watch the other video, and then come back. Okay, so I'm going to go over some of the things that were in that video that you have to know for Physics 30. So as you just learned, in Thomson's experiment, he had a gas-filled glass tube. Okay, and typically this gas tube is going to be filled with helium, but it could be a different gas. It doesn't have to be helium. And we're not going to look at why that gas is there today. We'll talk about that in a few lessons. And then inside of the glass tube, we have 2 pieces of metal. So one of the pieces of metal is called the cathode, and the other one is called the anode. And what Thomson noticed is that if you connect your metal plates here to a source of electrical potential. So that really just means a battery or some kind of power source. You would end up getting this glowing green ray that traveled from the cathode to the anode. Now, we know today that that ray ended up being electrons. But when we're studying this experiment, you have to put yourself back into Thomson's mindset, and you have to remember electrons hadn't been discovered yet. So Thomson didn't know what this glowing green thing was. That's what he actually was trying to figure out. He was trying to figure out what was that glowing green ray? What was it made of? And for now, okay, because this ray is coming from the cathode and going towards the anode, he decided to call it a cathode ray. So Thomson started trying to figure out what cathode rays are. Now, the ray glows inside the tube. So some people thought, oh, maybe the cathode ray is light. Maybe it's made up of photons that are moving from the cathode to the anode. The problem is, Thomson figured out, if I just go to the next slide here, he figured out that if you hold a magnet next to a cathode ray, the cathode ray will actually change its path while it reacts to the magnet. Okay, and magnets don't deflect light. If you hold a magnet up to a light bulb, it's not going to change the behavior of the light at all. And so cathode rays cannot be light. They're not just photons. So what Thomson guessed instead is that cathode rays might be pieces of the atoms that make up the cathode metal. So just to visualize that, say here you have a piece of metal, okay, or also known as your cathode. Let's say that this cathode is made of silver, just for example. It could be a different metal, but we'll just use silver as an example here. Well, that means that this metal has a whole bunch of silver atoms in it. Okay, and what Thomson hypothesized is that maybe something inside of the silver atoms is actually coming out of the atoms, and this little piece of a silver atom is what's making up the cathode ray. So pieces of the atoms that make up the cathode metal are the cathode rays, or at least that's what Thomson guessed was happening. So he decided to experiment a little bit more with cathode rays, and he found that most of the time cathode rays travel in a straight line. So if I just draw this picture here, again, I'll just make a little sketch of it. If we have a tube, okay, if the cathode rays are traveling in a straight line, this is what they're doing. So they're coming from the smaller end of the tube, so this is your cathode, and they're traveling over here towards the anode. And if you put a little cross, so this is actually called a Maltese cross, but that's not important. If you put a little cross inside of the tube, you'll end up with a shadow over here. And because you get a nice crisp shadow, you know that the cathode rays are traveling in a straight line. But then, as I kind of alluded to earlier, if you take your cathode rays and you hold a magnet nearby, the cathode rays will actually deflect in a circular path. So that tells us about what cathode rays are. If you think back to earlier in the course, what type of particle will move in a circular path in the presence of a magnetic field? And you should be thinking, oh, it's charged. So because we know that cathode rays move in a circle, we know that cathode rays must be made up of charged particles. Now, what I'd like you to do is pause the video again and go watch this YouTube video, and then come back. Okay, so hopefully you've watched the YouTube video. What you were supposed to get out of that is that not only are cathode rays charged, but from using the third hand rule, you can actually figure out that cathode rays are negatively charged. So cathode rays are negatively charged particles. So this is just showing that again. So when there's no magnet, the cathode rays move in a straight line. When there is a magnet, they are bending into a circle shape. Now, I know that doesn't look very much like a circle, but it's just because the circle is too big to fit in the tube. If the tube was bigger and we could extend this, you would see a circle shape happening like that for your cathode rays. Okay? Now, the other thing I'll just mention, cathode rays can be deflected by electric fields as well as magnetic fields. In Unit D here, we're just going to look at what cathode rays do in magnetic fields, but an electric field would work as well. The difference is that in a magnetic field, the cathode rays would be in circular motion, because we learned earlier in the course that when charged particles go in a magnetic field, they move in circles. But if the charged particles go into the electric field instead of a magnetic field, then it actually wouldn't be circular motion, it would be projectile motion instead. But we just studied the circular motion case here in Unit D. Okay, another thing that Thomson did when he was trying to figure out what a cathode ray actually is he calculated the charge to mass ratio of cathode rays. And the way he did that was with this apparatus here. So this apparatus has coils in it, okay? So this is coils of wire. What happens is when you run a current through the coils of wire, they make a magnetic field. So I'm going to say here, this is coils of wire making a magnetic field. And you can control the strength of that magnetic field right here by adjusting the amount of current flowing through the coil. Okay, and then what we have here is a glass tube, and inside the glass tube we see a circle. That's the cathode ray. Okay, and what Thomson noticed is that you could make the radius of this circle, so you can measure that radius there. You can make the radius of the circle bigger or smaller by changing the voltage. So what was actually happening is, remember that we have that formula, voltage is equal to change in energy over charge. From that, he was able to figure out the speed. And we're not going to look at the details of that right now. So this can be used to find speed because it's a little bit complicated. But basically, from this apparatus, Thomson knew 3 things. Okay, so if we list the things that are knowns, the value of R, which is the radius of the circle, is known. The value of B, which is the magnetic field inside the apparatus, that's known. And the speed of the cathode rays was known. Okay, and so what Thomson did is he was like, okay, I'm going to try to calculate the charge to mass ratio for the cathode rays. The reason that he calculated charge to mass ratio is that he didn't have enough information to just calculate the charge, and he also didn't have enough information to just calculate the mass. So this is what he did. So he would say, okay, we have charged particles in a magnetic field. Whenever we have charged particles in a magnetic field, we start with Fc equals Fm. Fc is mv squared over r, and Fm is qvb. And then what we'll do is we'll cancel out v. So right here, this speed cancels with one of these speeds. And then we'll rewrite what we have. So mv over r equals qb. Now, if you look at the equation that I've got here, okay, remember I said Thomson knew the value of v, he knew the value of r, and he knew the value of b. The only thing that was missing was M and Q. So what he decided to do is to actually calculate Q over M. So what we'll do is we'll divide both sides by M. So we're going to have V over R equals Q V over M. But I don't want QB over M. I just want Q over M. So now I'm going to divide both sides by V. Or by B, sorry. So V over BR is equal to Q over M. And so using that piece of equipment that was on the previous slide, Thomson was able to calculate the charge to mass ratio for the cathode rays. What he found when he did that is that the charge to mass ratio for a cathode ray was about 1,000 times bigger than the charge to mass ratio for a hydrogen atom. And so this means one of two things. Either cathode rays carry a huge charge, or they have a very small mass compared to hydrogen. Because think about this. If you have Q over M, if Q over M ends up being a big value, which it was for cathode rays because it was 1,000 times bigger than the mass than the charge to mass ratio for hydrogen, there's two ways to get a big value for a charge to mass ratio. You could either have a very big value for Q, or you could have a very small value for M. Now, we're not going to get into the details of why because it's not important, but based on other work that had been done at the time, Thomson was able to figure out that the reason that Q over M is so large for cathode rays is not because cathode rays have a big charge, but rather because whatever particles are making up a cathode ray have a very small mass. The other thing, just to note, is that the value of Q wasn't known until later, until 1913 from the Millikan experiment. So here we go. We've figured out here, okay, going back to this slide for a second, that the mass of a cathode ray particle is less than the mass of a hydrogen atom. Okay? And so, this is the important part. If that's true, since hydrogen is the smallest atom, then cathode ray particles are smaller than a hydrogen atom, and therefore they're smaller than any atom. So just revisiting that again, this slide shows that the mass of a cathode ray particle is less than the mass of a hydrogen atom. So we know that whatever is making up the cathode rays is smaller than hydrogen atoms themselves. But since hydrogen is the smallest atom to begin with, we now know that we've found something that's smaller than an atom. So that disproves what Dalton said. Remember, Dalton said atoms can't be broken down into something smaller? Well, Thomson just showed something that's smaller than an atom exists. Okay, a little bit more evidence that we have to look at. Thomson repeated this experiment over and over again. So if we go back up to here, okay, you can't really see it in the picture, but there's a piece of cathode metal somewhere in this apparatus, and you can change out that cathode to be a different type of metal. So when you first do the experiment, you could make your cathode out of silver. And then you could repeat the experiment, and this time you could use a cathode made out of gold. And what Thomson found is that it didn't matter what material was being used for the cathode. Every time he repeated the experiment, the value of Q over M was always the same. Okay? And so what he was able to conclude from that is that all atoms contain the same small particles. So remember, what Thomson said is that it's pieces of the cathode atoms that actually make up the cathode rays. So basically what he's showing here is that let's say you have a cathode made out of gold. Well, gold contains these cathode particles, because when you do the experiment with gold, you see a cathode ray. Let's say you do the experiment with silver. Well, silver also contains cathode particles, because when you do the experiment, you see a cathode ray. But you have to have some way of proving that the cathode particles coming out of gold are the same cathode particles that are coming out of silver. And the way that you do that is that if you can show that because these particles have the same Q over M, then that must mean that the cathode particles coming out of gold are no different than the cathode particles coming out of silver. They're the same type of particle in either case. And so, as I said, this means all atoms, it doesn't matter what the cathode is made of, all atoms contain these cathode particles. Okay, so to summarize, we've learned that cathode rays are a stream of negatively charged particles. The reason that we knew they were negative is because of the third hand rule. Okay, and the reason that we know that they're charged is because of the circular motion that they make in a magnetic field. Okay, these particles are smaller than atoms. The reason that we know that is because they have a large Q over M value. All atoms contain them, and they are the same in every atom. This is because Q over M is the same for all cathode rays. Okay, and so when we put all of this evidence together, what we find is that a fundamental or important piece of an atom must be these negatively charged subatomic particles that are making up the cathode rays, and instead of calling them cathode rays, we now call them electrons. So cathode rays are electrons. So the important thing, okay, that Thomson discovered is Thomson really discovered the electron. Okay, last thing we have to look at. So how did Thomson actually visualize the atom now that he's discovered the electron? So sometimes you might hear this called the plum pudding or the raisin bun model. If you look at this raisin bun here, we have a bunch of dough, and embedded in that dough we have raisins. Thomson pictured the raisin bun as a whole to be like the atom. The dough he pictured to be positively charged, and the raisins he pictured to be the negatively charged electrons. Now, we just have to talk about how Thomson knew that atoms had to have both positive and negative in them. Well, everybody knew, even before Thomson's experiment, that atoms are neutral, because most of the time we don't see objects attracting and repelling, right? So most objects are neutral, and that must mean the atoms that make them up are also neutral. So Thomson was like, okay, well, I've discovered these negative electrons. If atoms contain negative electrons, then they must also contain positive stuff in order to cancel out the negatives, because overall we know that the atom has to be neutral. So that's how he pictured it. And then this is just another picture of how the atom might look in the Thomson model. So you have your positively charged matter, so all of the red stuff is supposed to be positive, and then embedded in that we have our negative electrons.